Hello everyone, Assalamualaikum and good evening from Malaysia and good morning for Germany. I am Dr. Muhammad Najib bin Jamaluddin of the School of Biomedical Engineering, your host for today. Alright, seems like I'm traveling, but in this era of 4IR, everything is possible right now. Alright, so without further ado, I would like to invite Professor Dr. IR Dr. Rafiq to introduce our distinguished lecture series of Professor Haueisen. Please, Prof.
Thank you so much, Najib. Thank you so much for chairing the session. I can see that you get caught in the traffic. Assalamualaikum. Hello, welcome everyone. Welcome to our 22nd UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering, University Technology Malaysia. Today, it is my utmost pleasure to welcome Prof. Yen Haueisen from Technical University Ilmenau, Germany. A bit about our presenter today. Yen Haueisen is a full professor since 2005 and chair of the Institute of Biomedical Engineering and Informatics. He obtained his MS and PhD in electrical engineering from Technical University Ilmenau, Germany, and completed his habilitation in 2003 from the same university. He has authored 260 peer-reviewed scientific articles with an ISI H-index of 31 and a citation of close to 4,000. He is the editor of 3 books and 4 journal special issues. Yen is also a prolific inventor with 19 granted patents. He is a member of editorial board in scientific journals Brain Topography since 2018 and Frontiers in Human Neuroscience since 2017. He is also associate editor for journals Medical Physics since 2010, Biomedical Engineering since 2006, and Biomagnetics Research Technology between 2004 to 2008. He is the chair of the board of the notified body of the EU number 0118 at the Thuringian State Authority for Metrology and Verification 2007-2013 and a member of the Saxon Academy of Sciences since 2014. So that is a biography of our speaker. Here now is Professor Yen Haueisen from Technical University Ilmenau, Germany, with a talk entitled Resonance and Entrainment of the Brain. Professor Yen Haueisen, over to you.
Thank you very much, Professor Rafiq. It's a great pleasure to be here. It's a great pleasure to give this talk in the Distinguished Lecture Series at UTM. As some of you might know, I have been visiting UTM a number of times, and it's been always a very enjoyable and very beautiful time over there. But nowadays, due to the pandemic, lectures are more and more online, and therefore it's a great pleasure for me to give you this lecture today about resonance and entrainment in the brain. And I would like to start this lecture with a few words of introduction, because the topic is maybe for some of you a bit far away. So what is it, resonance and entrainment in the brain? What we have is a definition here for resonance, and when you look from it in a point of view of electronics or electrical engineering, then it is quite similar in terms of what we define as resonance and entrainment in electronics and similar. But the difference is that the substrate is not an integrated circuit, but the brain. So what you see in terms of resonance is an enlarged brain response in terms of amplitudes when you apply a stimulation frequency which is in the range of a free running brain rhythm or in harmonically related frequencies. And a free running brain rhythm is what everyone has, and not just one, a number of them. A typical one is the so-called alpha frequency, which is a typical frequency for each person. And this frequency is slightly different for each person. So some have an alpha frequency of about 10 hertz. Some might have like 9 or 12 hertz, that depends. And this frequency is called an idling frequency. So whenever you relax and whenever you close your eyes, you typically have a rhythm like this, very visible in your recorded electric or magnetic data, electroencephalography or magnetoencephalography. Now the second term is called entrainment, and again this is quite similar to what we have in electrical engineering. It is frequency locking to a free running brain rhythm with a specific stimulation frequency. And this goes actually back to the Dutch physicist Christian Huygens, who about 400 years discovered this frequency entrainment with the pendulum clocks. You might remember this from your basics physics course, when you have two pendulum clocks and they are sitting on a board, on a wooden board, for example, then they synchronize their pendulum movements. So this is what is called entrainment, and this also takes place in the brain, as we will see as we move along. So here are two examples of that. So this is a paper from 2001 from a colleague who published here a study where he sort of tested different frequency, and I picked out here only the 10 hertz and the 20 hertz example. What you see is with the 20 hertz stimulation frequency, your signal in the brain is much smaller compared to the 10 hertz stimulation signal. And you see this also in the frequency response down here. This frequency peak is of course much higher than the one here. So this is a typical example of resonance in the brain. Here is an explanation for the frequency entrainment in the brain. So what we have is a input frequency, you can think of any sort of stimulation that might be, for example, auditory stimulation, like a beat going on, dum, 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 and so on. It might be visual stimulation, or it might be also somatosensory stimulation. So like think of tapping in a certain frequency, for example. And now when you have a certain stimulus amplitude and a certain stimulus frequency, and you have a omega 0, which is the rhythm of the, or the frequency of the brain oscillator itself as such, then you have a so-called Arnold tongue. Arnold was a Russian mathematician who gave the name for this. And depending on whether you are inside the Arnold tongue or outside, you get an entrainment or a no entrainment. And that means stronger stimuli are more likely to also catch frequencies further away, stimulation frequencies further away from the actual free running rhythm of the brain as such. So with this, we are sort of able to have a look at, say, certain experiments, which will then give us statements about the entrainment or the resonance, as depicted on the previous slide, for different brain situations, I would call it, different brain states, if you like. Now, we do this by measuring electric and magnetic signals of the brain. What you can see here is the typical situation. You have some sort of activity going on in the brain, and you have measurements of the magnetic field outside. You see a pickup loop here of a magnetometer outside here. And you see two electrodes for recording. Those recordings are called magnetoencephalography and electroencephalography, and they measure potential differences or the magnetic flux, actually, of the activity going on in the brain. Now, why these measurements and not any of the others? You probably know that there is functional magnetic resonance imaging, there is positron emission tomography, there is near-infrared spectroscopy, and so on. However, all the other imaging modalities, they have one big disadvantage. They are slow. We're talking about seconds to minutes, while for the EEG, MEG, we're talking about micro and milliseconds. So that is really something different. And this is needed for the rhythmic brain activity. So this is the reason why we choose this type of technology for recording this activity. Now, what we do or specifically is what you can see here on this slide depicted. We use a technique which is called intermittent photic stimulation. And it is a very simple technique, and it's actually also a very old technique. Intermittent photic stimulation is a flashing light. So you see this flash depicted here every so many milliseconds. And this flashing light is applied to the eye. So this technique as such is used for a long time in the diagnosis of epilepsy, for example. So it is a technique about 50 years old or so. Now, when you apply this, then you get indeed both resonance and entrainment. So the visual system consisting of the eyes first, and then the visual cortex, some processing stages in between. They are a system where you can record indeed resonance and frequency entrainment effects. And what has been recently proposed, and what is one of our motivations to do actually this work, is that this intermittent photic stimulation might be also a useful biomarker in depression. So patients with major depression, this might be a biomarker for early detection, for example. Now, how does it, when you take a closer look at the literature, then you see that there is quite a diversity of results. And one result which puzzled us a while ago, when we started this research, was that we had two different types of stimulations which were used in previous publications. So there were high intensity flashes and there were low intensity flashes. In one case, people found resonance. In another case, they did not find resonance above 12 hertz. So they find some resonance, but not above 12 hertz. While those guys here, they found resonance all the way to up 80 hertz or so. Now the question is, why is this discrepancy here? This discrepancy is something which we thought might be related to scotopic vision. So there are two types of vision, which you're probably aware of. The one is the photopic vision with the cones as the main receptors, the main sensors, and that is in light situation. So right now, for example. And the other one is scotopic vision, and that is in the dark. So the rods are then the main receptors, the main sensors, so to say. And those rods, they have a different flicker fusion frequency. So in other words, when you are in a light situation, you can recognize flickering lights all the way up to about 100 hertz. While in a dark situation, you can recognize flickering lights only up to about 15 hertz. Then it basically ends. Now, our hypothesis was that this is indeed the difference between the discrepancies we found in the literature, namely that we have a separate cone-driven input and a rod-driven input. So now, when you do this, then you would, of course, expect that in the literature you find also statements about the amount of light which is applied. But no, this is unfortunately not the case. In most cases, well, actually in this case, in all cases in literature, there was no statement about candela per square meter whatsoever. So now what we tested then is in a real scotopic setup, whether there is a resonance and entrainment. And this is what I would like to show you with a small study here, which we did on 12 healthy volunteers with different stimulation frequencies. And the stimulation frequencies are actually tailored to each subject. So when you have, for example, a alpha frequency of about 10 hertz, then we start using this alpha frequency. We start with 0.4 times 10 hertz, and we end with 2.3 times 10 hertz as a stimulation frequency. Similar to subjects with 11 or 12 hertz as an alpha frequency and so on. So it's an individual stimulation frequency. We do this with stimulation with eyes closed, and we do this in real scotopic vision because we actually measured the luminance, and it was about, as you can see here, 10 to the minus 4 candela per square meter. The measurement was done with a MEG and EEG system in combination. Now, when you look at the different stimulation frequencies, they have to be applied, and we did this in a random fashion. So we had blocks with different frequencies, F1 to F20, but they were randomized, of course. And in each of these blocks with each frequency, we had a train of different stimulations. So a typical on-off, as I said, stimulation with 40 periods of light flashes. And this was repeated 30 times. Now we can, of course, average this afterwards. This is how it looks like when you look at the experiment. You see the MEG setup. The guy or the subject here is sitting inside, having the LEDs, or actually the light stimulation is transmitted by fiber here in front of the eyes. Now, when we use this, we use actually optical fibers, as I said, and a diffuser. This diffuser allows to have a distribution of the light instead of just a focal light. Then we had radiometric measurements done. As I said, we had eye lead transmission curves, and we computed the luminance, and this is actually in real scotopic vision, as indicated earlier. Now, data analysis. What can you do with the data? So first is averaging a time domain, and this is, of course, very simple. You take the 30 trains, average them, and see what's coming out. So this we did, of course. Then the second thing is frequency domain analysis, and especially the alpha peak ratio, which was introduced in this paper here, which I will show you in a minute. It is straightforward, as I said, frequency domain analysis. Then we did a spatial temporal analysis with topographic matching pursuit, as indicated in this paper here. So the technique is described here in this paper. And then we did a spatial correlation analysis with those TMP atoms, topographic matching pursuit atoms, as indicated in this paper. And finally, we also did source localization on that. So we wanted to know where in the brain this activity is actually happening. And last but not least, we did a canonical polyadic decomposition, which was actually published recently, about 3 months ago, actually. Now, having a look at the results, what you see here is the average in the time domain. So you see 4 different stimulation frequency, 0.5 hertz, 1 hertz, 1.3, and 2.0 hertz. And what you can see already is that we have a nice resonance effect, so very strong amplitudes compared to baseline. At 0 is the stimulation onset. So here is baseline, nothing is happening. And once we start, then we actually go up here and have a nice resonance, but even continues slightly after the end of stimulation. In this case, for 1 alpha, same thing, very nice resonance effects. And it continues actually a bit more after the end of stimulation. You can see this here. there is end of stimulation is here, and we have a continuation with a sort of slope down. If you look at 1.3, then we see much less, and if you look at 2.0, then we see pretty much no resonance effect whatsoever. So this indicates already that the separation of the cone and rod-driven input is quite well possible. So this is a very nice indication. And this first peak here is on response. I will come to this in a minute. Now, having a look at the frequency domain, so you see the frequency amplitude indicated here. We look at baseline alpha, we look at 2.0 alpha, 1.95, 1.0, 0.95 alpha. And what you then see as an alpha peak ratio is the alpha frequency of the peak in the stimulation situation over the alpha frequency peak in the spectrum of baseline. So this is what you see here indicated in blue, this value and this value. Now we can have a look at this all together. This is for all subjects. We published this 4 years ago. This is for all subjects and all stimulation frequencies. So here you see now all of the stimulation frequencies we did for the subject, starting from 0.4 all the way to 2.3. And what you can see is that around 0.5 alpha and around 1.0 alpha, we have significant increases in the alpha peak ratio, where in the rest we have more or less suppression, right? And there is nothing going on here for the 2 alpha situation, which would be a harmonic, of course, as well, similar to the 0.5 subharmonic. But obviously there is nothing to be recorded here in terms of the alpha peak. Now having a look at topographic matching pursuit. Topographic matching pursuit is a matching pursuit technique. Matching pursuit is a technique which uses a large dictionary and then decomposes the signal in a time frequency fashion. However, we do this differently here with a topographic approach. So not only a temporal approach for time frequency decomposition, but temporal spatial approach. So you use also the spatial domain. That means your activity distributed here on the head. You see the nose here, the ears left and right, and you see the distribution in this case for the magnetic signal, for the MEG signal. So all the values are in picotesla. And when you use, this is the original signal, and this is our approximation with a specific TMP atom. So you see this here, the both the time and the spatial distributions are quite well. Now we can do this, of course, for all of the subjects. We can do this for all of the frequencies, and we can do this, of course, across the entire signal range. And when we do this, then we can use correlations between the general topographic result at 1 alpha and all the rest. And this is what you can see indicated here. So you see a correlation coefficient curve, which has two different up and down phases, which are indicated with 1 and 3 here, and a plateau in the middle. So the up phase is basically the start, which is called engagement phase of the oscillator. Then we have the plateau, and then we have the disengagement phase after the end. And this disengagement phase, as well as the engagement phase, has some variability across subjects. When you look now at 2.0 alphas, you see basically nothing, right? There is not much going on here. So in other words, at 2.0 alpha, we are beyond the flicker fusion frequency, so the rods can actually not follow the signal anymore. One more thing, which I said earlier, is the so-called on response. Now, consider a flickering light where the frequency is beyond what you can actually perceive, then you would see just a light going on, staying on for a while, and then going off again. And that would, of course, have two responses, namely a switching on response and a switching off response. And this is known in electrophysiology, and this is actually what we find here. This is this on response, which you can see here. And actually, after the end, you see also an off response, which is indicated here after the end of stimulation. And you see this only for the frequencies which are beyond the flicker fusion frequency. Interestingly, the general topography is similar to what we see here for the main stimulation, and that is actually expected because it is the same brain area where this activity is coming from. Now, this off response and this on response, they also have latencies, and this latency is about 200 milliseconds in this case, and that means indeed a typical on response. So that is consistent with the literature in this case. Similar with the off response, as you can see here, that off response has a similar topography and it has a similar latency. Now, having a look at frequency entrainment, you can see this indicated here, so that we have for our frequencies around 0.5 alpha, about 1.0 alpha, quite some frequency entrainment. Of course, not for all of the subjects. You can see there is some left over. We'll address this in the last part here. And that part basically is ending at 1.3. So there is no frequency entrainment whatsoever beyond 1.3 alpha. And that is exactly what we were expecting in terms of our hypothesis. For a scotopic stimulation, there should be, beyond the flicker fusion frequency, no entrainment anymore. And this is actually the case. Now, in terms of where does it come from, we did a source localization. I will not go into the details because that is, say, a talk on its own. What you can see here is a view on the brain. You see the view on the brain from the top view, from the back view, and what you see indicated is in blue, the Brodmann area 17, which is the occipital area of the brain, which is the one where you actually process visual stimuli. And you see those poles here. They are indicating the activity which we are localized. So at this point and at this point, left and right. Why left and right? We did stimulation on both eyes. So we would expect also left and right activity. So that is consistent. Now, for the last part, I would like to draw your attention towards tensor decomposition. So I think all of you are familiar with PCA and ICA techniques because they're quite common these days. Principal and independent component analysis are a typical tool which you use in many areas of technology. When you think of a multivariate data set where we have, for example, both EEG and MEG, it is sort of difficult to actually apply ICA or PCA in the same situation. And one way out is tensor decomposition. Tensor decomposition is basically an open up. Is sometimes also called canonical decomposition, depending on the field. So what we have here as a basis is we have a number of channels in MEG, a number of channels in EEG, and then we do a time frequency decomposition. So we have those basic dimensions, frequency, time, and channels for the two recording data sets, MEG and EEG. Now the frequency the frequency decomposition was actually done with a complex Moore-led, wave-led, but that can be done also with other approaches. Time varies, that is also important. We always do a number of stimulations, and since we do this in different frequencies, time varies. So each of our conditions, each of our stimulations has a different time length, which also complicates analysis quite a bit. Now, the tensor decomposition gives us a decomposition again in the space, time, and frequency domain. And this is what you can see here depicted for a stimulation frequency of 0.55 alpha for one participant, participant number 1 in this case. And what you can see here first in the upper row is the MEG recorded signal. Down here you see the recorded EEG signal. And then we see the decomposition into two components. You can see them both here in the spatial domain. And as you can see, they're rather similar. They're not identical, but rather similar. And then you can see the decomposition in the frequency domain. And here we see a clear distinction at 0.5 alpha and at 1 alpha. And you can see a decomposition in the time domain, where we basically still have the engagement, the plateau, and the disengagement phase. So it's the same thing as we have seen before. And that is something which we can now use to actually draw for all of the participants and all of the components a scatter plot for normalized stimulation frequency and the normalized frequency obtained from the analysis. And this is what you see here as a group analysis across all subjects. And what you can see is we have two different lines. The two dashed lines are reference lines. They are representing the stimulation frequency and its harmonics. So this is two of the second, and this is the main. And what you can see, we have crosses. Those are signals where we really have recruitment, where we have also this entrainment. And then we have other ones, non-recruited. Those are the ones you can see here. And those are distributed in two frequency bands. We see one here in the 1 alpha and in half alpha, which is theta band, basically. And this is something interesting, because what you cannot see here in this slide, but I will show you on this slide here, is that we either get an entrainment for the subjects or a first harmonic entrainment, or we get an independent oscillation in the individual alpha or theta band. So at roughly 10 hertz, roughly 5 hertz, right? Depending for the subject. So that is an interesting fact. And even more interesting, the relationship between the alpha and theta band oscillation are reciprocal. That means only you see them only in one band, not in two bands. So either you see an alpha activity or you see a theta activity, but not both of them. And that is interesting, because that might serve indeed as a biomarker, this differential result you get for the different subjects, that might serve as a biomarker for further investigations on subjects or on patients, which we are currently planning. So back to our original hypothesis, the scotopic vision is something where we do actually find that resonance and entrainment in the brain is really there, also in photopic, and therefore potentially also in mesopic vision. Mesopic is the area between photopic and scotopic, up to about 15 hertz, which is the flicker fusion frequency, right? And there is no resonance, no entrainment above this 1.3 alpha, which is this 15 hertz roughly. Instead, we find on and off responses. So in conclusion, we have two different inputs for the oscillator network, a cone and a rod-driven input. And we suggest for all future measurements that indeed photometric measurements should be done for such studies. So with this, I would like to thank you for your attention, my co-workers and PhD students for their work, as well as our financial supporters from the EU / the German Research Foundation. And with my last slide, I would like to do an announcement for a activity which is going on in a few days, actually starting on August 5, which is our International Summer School in Biomedical Engineering, which will cover actually non-invasive dynamic brain imaging for infants, children, and adults. You don't have to be on site. I mean, there are some people on site, but there are also a number of people in the internet. So feel free to register for this summer school. The link here will get you to the summer school. Yeah, thank you very much for the attention.
Oh, thank you, Professor Haueisen, for the great presentation on the topic of brain entrainment. Right, so we welcome any questions from the audience. Right, so while we see if you have any further questions, so I myself would like to ask Prof Haueisen, other than entrainment using light, is it possible to also do entrainment of the brain using sound waves?
Yes, absolutely. Any type of stimulation can do so. Any type of stimulation will introduce resonance and entrainment when you do it at the right frequencies. So for the visual system, as I said, it's the typical alpha situation. In the somatosensory system, it's the so-called mu rhythm. Or somatosensory motor rhythm, that's also called. And similar also for the auditory. It works for all perceptions. Well, all perception, I'm not sure whether it is working for olfactory or gustatory. That I'm actually not sure. But for the three main ones, yes.
Mm-hmm. Right. Since that, like, I want to ask further things like, because sound, the frequency of sound starts from, let's say, 20 hertz to up till maybe 16 kilohertz, right? So, but if you want to entrain the brain, let's say for alpha is around what 7 hertz, right? It's around that frequency. So I've read about doing the brain entrainment of the alpha brainwave using the something like a binaural beat. So which means that if you make your right ear to listen, let's say what 40, I would say maybe 1 kilohertz, and the other ear you make it to listen 1008 hertz. So the difference is will induce 8 hertz brainwave. So what is your opinion on that? Something like a topic on binaural beat, to do the brain entrainment,
Mm-hmm. I think you can. Well, I'm pretty convinced that you can do this. I'm not an expert in auditory though, so I cannot tell you really something substantial on how this will work or what the hypothesis might be for this, how it will work. But I think the experiment setup you outlined, that is doable from my side.
Mm-hmm. Yeah. So, Prof, another question from me also while waiting. A question from the audience also. What is the main purpose of doing the brain entrainment? I mean, the brain entrainment, yes. So, is there any healthy benefit? So, other than diagnosis, you see. So, is it also Is it also possible to make it as a therapy?
Yeah, there are some approaches. For example, I have recently talked to a colleague who is doing this for migraine patients. Maybe you know that migraine it's a special type of headache. So half-sided headache with a certain pattern, and migraine has been associated or is associated also with visual input being potentially difficult, but on the other side also with flickering light being potentially helpful. But I think this is not yet fully clear. So this colleague, he is using sort of goggles on those patients, stimulating with certain frequencies in the help of improvement for that type of patient. That is indeed something where you could use flickering light also as a therapy option.
Mm-hmm.
But right now, I mean, established is diagnosis, of course. So like an epilepsy or similar diagnosis with flickering light with this intermittent photic stimulation, that is well established, I can say.
Yes, yes. Well, Prof, also on the topic on the depression, right? To diagnose depression, do you have any more details on that?
Yeah, so one of the things which are associated with depression is changes in rhythmic activity also in the brain. So there are changes in the frequencies, there are changes in the responses with rhythmic activities in depression, which has been documented in the literature. And therefore, it seems likely that those changes are maybe detected early before you actually move or go into really severe depression. But this is still subject of investigation. So I'm not sure. This is, say, open field in a way.
Yes.
We are at the moment planning a study with one of our medical doctors on depressive patients with this type of stimulation, which will likely take place next year. Mm-hmm. From the literature, the situation is unclear, I have to say. It's unclear in the sense that there are some indications where you can set up hypotheses, but there is not yet convincing evidence whether it works or whether it will not work.
Right. So I think from this we can say that there is always we can always do research on this topic lah. There is more. There is many opportunities for us to explore on the brain entrainment topic, especially like myself, I'm doing on virtual reality, you see. But I'm doing on the effect of virtual reality, how to make objects in virtual reality to to affect your emotion or to affect your how to improve how your brain works, things like that lah. Right, Prof? Mm-hmm. And I can see that the MEG machine, so is it the equipment, is it in the University of Ilmenau or you're using it from some other facilities?
Yeah, the MEG machine is actually located in Jena, which is about 3/4 away from my institute here in Ilmenau. So it's like 3/4 by car to go there. So it's not far away. And I have a second group basically over in the neurology department. So the machine, the MEG machine, is part of neurology department actually. And we have, since I've been earlier working full-time in the neurology department before I moved here to Ilmenau, then I still have very good contacts, and we do studies together all the time.
Yes. That's good, Prof. Maybe, I think we have a question from an audience. So, Prof Rafiq, are you going to share on the screen? Yes, so we have a question from Amir Ahmad. So his question is the artifact removal considered for detection of these rhythmic activities using EEG and EMG signals? And if so, is there any specific technique that proved to be most efficient? Please, Prof.
Artifacts are a typical problem whenever you do such recordings. And yes, artifact removal is essential. I have not talked much about artifact removal in this talk here, but we do use artifact removal tools for conditioning of the data. So, for example, when you one of the things which is implicit artifact removal is when you do a matching pursuit or when you do tensor decomposition, we use only the top ranks. So like in tensor decomposition, we use like the first two ranks typically. That is actually not an easy situation because in some subjects you have actually 3 valid ranks in the tensor components. This is actually also one thing which one of my students at the moment is doing, namely trying to figure out how to optimally estimate the rank of such data. What is the optimal rank in tensor decomposition? But given the fact that we throw anything away which has lower ranks, basically does also some sort of artifact removal. What we do in addition is, of course, baseline corrections. That is necessary in most cases because you're likely to have drifts of any kind in electric recordings especially. And what we do, which I did not mention, for depending on the type of analysis, but for example, in the time domain analysis, we also had a Butterworth filter, for example, applied. So a bandpass filter applied. What we did not do is artifact removal from physiological signals, like, well, eye blinking, there are none, of course, but like EMG activity, we did not correct for. And the reason for that is that we have, in this case, only slight EMG activity because the people are sitting in a very relaxed situation. So they lean their head backwards into the helmet, and they have in addition a sort of a towel / support textile on their neck, so that they can really good, comfortably and relaxed sit in that machinery. So therefore, there was no EMG correction, artifact correction whatsoever in this case. And EMG was not actually so prominent in this recording, I have to say. Yeah, I hope this answers the question.
Yeah. So that the subject does not move, so does the subject needs to be sedated during this experiment that you have done? No.
No, they're not sedated. They don't get any tranquilizer or so. They are not sedated. They are just sitting there relaxed. So it's not something where you have where you give medication or something.
All right. So, Prof, we have another question from Amir Ahmad. Thank you. His question is: EOG signals used to aid the artifact detection, especially while recording the baseline.
I didn't get this. You say EOG, so electrooculogram, right?
Yeah, the signals from the eye, maybe, I think.
Yes. No, in this case, EOG was not really required to correct for because the recordings were done with eyes closed. So people were not blinking and not, well, moving the eyes, maybe, yes, but at least we did not correct for this, actually.
Yeah, so having the eyes closed and telling the subjects to relax, so there is no possibility of the eye affecting the measurement, right? Yes.
Well, at least I mean they still could move their eyes around, but they were instructed not to do so, and we actually did not control for this, I have to say. So I cannot really say whether there have been eye movements, but as a matter of fact, they were not really obvious from the raw data. When you do the EEG review, I mean, you scroll anyway through the raw data, and there was not an issue with that. I can tell for sure.
All All right. Okay, Prof. I think it's already 4:50 p.m. over here. We have our session for 50 minutes, and I think we can end our session right now. And I would like to thank Professor Dr. Engineer Habil Jens Haueisen from the Technical University of Ilmenau, Germany, for delivering on the topic of the brain entrainment. All right, and I will pass this back to Prof. Rafiq.
Thank you, Najib, for chairing the session, and thank you to Prof. Yen Haueisen. I just want to tell you this because I have one of my friends, one of my colleagues who is not a biomedical engineer and who saw the poster of this event, and he said that, you know, there must be a mistake in the words. It should not be entrainment, it should be entertainment. Yeah, so hopefully now he understands what an entrainment of the brain is. Thank you very much, Prof. Yen. Just to let everybody know who is watching this webinar throughout the globe, Yen Haueisen is our distinguished professor here in UTM. He has been working with us for so many years, and it is good to see him back, albeit via cyberspace, via online. So thank you so much, Yen Haueisen, for giving the lecture on the entrainment of the brain. So until next time, to all of you watching this webinar throughout the globe, thank you so very much for watching, and do stay with us. Don't forget to like, share, and comment our Facebook. We have so many distinguished lecture series for you. Until then, bye for now.
Yeah, thank you very much. Also from my side, thank you, Rafiq, and thank you, Najib, for sharing this. It's been a wonderful experience.
Thank you. Bye-bye.
Thanks.